All right, let's dive right into this explainer. Today, we are completely taking the mystery out of Verilog. If you've ever felt a bit intimidated by hardware description languages, don't even worry about it. We're going to treat this whole thing like a builder's journey. Together, we'll go step by step. We'll start by learning the absolute basic syntax, basically the ground rules of our construction site, and work our way all the way up to writing your very first fully functional hardware module,
A multiplexer.
Let's get started. Here's the roadmap for this explainer. 1. Basics of Verilog syntax. 2. Logic gates and primitives. 3. Structural versus behavioral modeling. 4. Building your first multiplexer. And 5. Verilog operators.
Section 1. Basics of Verilog syntax. Laying the foundation. Okay, before we can start wiring anything up in our Altera Cordis Prime environment, we really need to know the ground rules, the basic language rules that the compiler will actually accept. Verilog has a few simple but absolutely crucial rules you got to keep in mind. First off, it is case sensitive. So a signal named with a lowercase x is a completely different thing from a capital X. Make sure you watch out for that. Also, when you're naming your modules and signals, the name absolutely has to start with a letter. After that first letter, you're free to use any combination of letters, numbers, underscores, and even the $sign. Another really great feature is that whitespace characters, like spaces, tabs, blank lines, they are completely ignored by the compiler. That means you can format your code so it looks clean and is super easy to read. Oh, and finally, whenever you want to leave a note for yourself or your team, you just start the line with a double slash to make a comment. Simple, right? Moving on to Section 2, logic gates and primitives, our raw materials. Now that we have our naming conventions locked in, let's look at the actual pieces we use to build hardware logic. You see, Verilog includes a built-in set of gate-level primitives, and honestly, this beautifully illustrates just how straightforward the jump from traditional hardware design to Verilog can be. If you think about the classic standard schematic symbols for a 2-input AND gate or a 2-input OR gate, well, in Verilog, you don't need to overcomplicate it. You just call them by their functional names, AND and OR, written entirely in lowercase. You instantiate the gate, declare its output, and list its inputs. It is literally a direct one-to-one mapping from the physical schematic straight to your code. And the exact same logic applies to slightly trickier primitives, like the NAND gate and the XOR gate. By just typing NAND or XOR, you're telling the compiler to reach right into its toolbox and pull out those exact physical logic structures. It's so cool because a simple, functional word in your code represents real, physical inputs and outputs sitting on the silicon. Section 3. Structural versus behavioral modeling. 2 ways to build. So once you have your gates, you have to decide how you actually want to put them together. And this is a massive point. Verilog offers us 2 completely different architectural philosophies. Think of structural modeling like wiring a house by hand. You, the designer, explicitly define every single gate and connect them wire by wire. It's super detailed, it gives you ultimate control, but man, it can be incredibly tedious for larger circuits. On the flip side, we have behavioral modeling. Think of this one like writing a smart home recipe. Instead of manually running all that copper wire, you just describe what you want the circuit to do using logic expressions. You tell the compiler the behavior you expect, and the software automatically figures out the absolute best way to wire those gates together in the background. It's a real game changer. All right, Section 4. Building your first multiplexer, the capstone project. Let's apply everything we've talked about to a highly practical beginner module. To really grasp why we need a multiplexer, ask yourself this. How do we route 2 entirely different data sources into a single output? And how do we control which one gets through? Imagine we have 2 separate streams of data coming in, input x1 and input x2. We only have one output path, so we need to choose between them dynamically on the fly. We do this using a selection control signal, which we'll just call S. And that right there is the core definition of a 2-to-1 multiplexer. Before we write a single line of code, we always define our goal, and a truth table clearly maps it all out for us. Look at our selection signal, S. If S is 0, the output of our circuit, which we're calling F, will simply be whatever value is sitting on input x1. But if S is flipped to 1, the output changes to match input x2. It's basically a digital traffic cop directing the flow of data. If we were to design this using that structural approach, wiring the house by hand, we have to map out the exact logic gates required to fulfill that truth table. To route x1 and x2 based on our signal S, we actually have to route S through a NOT gate to invert it for one path, feed those signals into 2 separate AND gates, and then finally combine their outputs using an OR gate to get our final output F. Now, what's really fascinating is seeing how that exact schematic translates directly into structural Verilog code. Notice how every single gate we just talked about is explicitly called out here. We declare our module, our inputs, our output, then we manually type out the NOT gate, the 2 AND gates, and the OR gate. We even have to invent intermediate wire names, K, G, and H, just to connect the output of one gate to the input of the next. It works perfectly, sure, but as you can see, managing all those individual wires is just a ton of manual labor. But what if we step back and use behavioral modeling instead? Using the assign keyword, we can write a continuous assignment statement. We completely drop the manual gate instantiation. We drop the intermediate wires. Instead, we use logic expressions. We literally just tell the system assign the output F to be not S and X1 or S and X2. We just handed the compiler the smart home recipe, and the software is going to build that entire schematic we saw earlier completely by itself. Actually, we can make this even more intuitive. By using what's called a procedural statement inside an always block, we can write code that reads almost exactly like plain English. Just listen to this. Always, when X1, X2, or S changes, if S equals 0, F equals X1, else F equals X2. That perfectly matches the fundamental rule we established way back in our truth table, and it completely abstracts away all those complex logic gates underneath. This right here is exactly why behavioral modeling is so incredibly powerful for beginners writing their first module. Section 5. Verilog Operators, your cheat sheet. To help you write these super efficient behavioral expressions, let's take a quick look at the robust set of operators that Verilog gives us. This cheat sheet breaks down the hierarchy of operators you're going to use on a daily basis. You have your bitwise operators like the tilde, ampersand, and pipe, which perform gate-level logic on each individual bit of a signal. Then you have logical operators, the ones with double symbols, and those treat the whole signal as a single Boolean truth value. You've also got reduction operators that compress a multi-bit vector way down to a single 1-bit result, standard equality checks to see if two signals match, and of course, arithmetic operators for basic math. Definitely keep these in mind. You'll always want to know exactly which symbol to pull out of your toolkit. Oh, and one last crucial detail before we wrap up. When you need to specify literal numbers in your code, Verilog uses a very specific positional format. It looks a little bit strange at first glance, but I promise it's very logical. You declare the size of the number in bits, add an apostrophe, followed by a radix identifier, like B for binary or H for hex, and finally you write out the significant digits themselves. This strict formatting ensures the hardware always knows exactly how wide your data buses are supposed to be. No guessing allowed. So now that you understand the basic rules, the physical logic gates, and how to write that smart recipe for hardware using behavioral modeling, I want to leave you with this final thought. Think back to that super clean if-else statement we used for a simple 2-to-1 multiplexer. Knowing how clean and scalable that approach is, how effortlessly do you think you could scale that code up to build a massive 16-to-1 multiplexer? Imagine trying to wire that beast by hand structurally versus just writing a few intuitive lines of behavioral code. It really changes how you look at hardware design, doesn't it? Thanks for joining me on this explainer, and hey, happy coding!